How much weight are you dealing with in a leg press? You've probably noticed that you can lift way more on a leg press than you can on something like a squat. And while there are multiple reasons for that, this might be the biggest one. On a leg press, can the weight, even if you're not there, travel straight down to the ground? Can it travel through the leg press? Assuming your leg press isn't made of the flimsiest materials on earth. Hopefully not. Even if you're not there and nothing stops it, it will travel down the slope that it is on. It doesn't go straight down towards the ground, it goes along the slope. And along the slope basically means we're dealing with a triangle. So the first place we have to start when looking at a leg press is acceptance of the fact we're dealing with the physics of triangles and inclined planes. Let's write that bit down. So this is an inclined plane. Okay, so let's say we've got some weight on here. And for the sake of easy maths, let's make that weight 100 kilos. Gravity, if we remember, is going to be equal to 9.8 meters per second squared, and it's trying to head down. But, as we've discovered, it can't go straight through the leg press. It must travel down the slope. This force then has two components to it. An amount that is parallel, that comes down this slope, and an amount that is perpendicular to it, an amount that presses into the leg press. And we draw that with parallelograms. Hopefully you can see that that guy, and I've probably drawn that component up here, maybe a bit too long, he should really have been there, so let's rub that bit off and put him through there. And if you look at that, you can see we've kind of got a couple of triangles, and therefore this length is the same as this length. Actually, that's still a bit long. I haven't drawn that particularly well, but you get the idea. And so this force we're going to call mg parallel, which we're going to denote with two parallel lines. And this force is mg perpendicular, because it is perpendicular, making a T shape, to the plane of the leg press, to that line right there. Well, we're not going through the leg press, which means there is a certain amount of force that must be equal to the amount pressing into the leg press, pushing back out of there. And that is the same length as that guy, the same magnitude as that guy. So N here, the normal force, which is the amount of force pushing off of the leg press. N, let's call him over here, N must be equal to the inverse of mg perpendicular. So whatever number that is, that has to be the same. So if that's 10, that's minus 10. If that's minus 10, that's 10. They're the same as each other. So for the rest of our thing right now, we can assume they cancel out. I don't need to pay any attention to them because we're interested in the amount that is coming down the slope. So we're interested in mg sub parallel. So how much is mg parallel? Well, to answer that, we're going to need to go and visit Mr. Pythagoras. We're going to need some trigonometry. So we're going to try and remember so, ka, toa. Now, I didn't care about maths at school, and the only reason I started to care about this was so I could analyse things like this. So, let's recap for those of you, like me, who had no idea what that meant. So means the sine, that's why we get the S from. Sine of an angle, and we're going to come to that in a second, is the opposite, O, divided by the hypotenuse. Ka means the cosine of the angle, and that is the adjacent divided by the hypotenuse, and the tangent is equal to the opposite divided by the adjacent. What in the hell are opposites, adjacents, and hypotenuses? So we need, in order to answer this, an angle from which we look at things from. We're going to call this angle here theta, right? And so let's say that theta is equal to 30 degrees. We could decide whatever the hell that is, but let's go with 30 degrees for this particular one. Okay, from its perspective, what is opposite to it? There. That is opposite that guy. So this tells us we're starting to deal with the sine, or maybe the tangent, we don't know yet, but we're going to divide the sine by the hypotenuse. The hypotenuse is the long bit in a right-sided triangle. So this guy down here. So sine deals with the opposite divided by the hypotenuse. The cosine is adjacent to theta, so it's this length here, also divided by the hypotenuse. And the tangent is equal to the opposite divided by A, the adjacent. Well, we're interested in figuring something out. Who's this guy? How much is mg parallel? What's he equal to? How strong is he? Because that's what you're going to be pushing against, is the component of this that is coming down the slope. Cool thing of triangles. This angle here turns out to be exactly equal to this angle here between mg perpendicular and mg itself. And if you're not sure of that, draw one of these yourself, get your protractor out and measure the angles, and you go, oh shit, that's the same as that guy. Which means we can now use this to help us to know what these are. So from the perspective of this angle in between these two forces, mg parallel is going to be equal, because remember we're looking from here out, is going to be equal to whatever the opposite is, and we know what the hypotenuse is. The hypotenuse is mg. It's 100 times 9.8 meters per second squared. So mg, and this line here is the same as this, because together they make a rectangle. So this length is the same as this length. And so mg subparallel is equal to mg itself times the sine, the opposite divided by the hypotenuse, of the angle theta, which is 30 degrees. So mg parallel, the amount you're dealing with, is equal to that. Calculator time. Whack this guy on. 100 kilos times, that's mass, times gravity. So 100 times 9.8 times the sine of 30 degrees gives us mg, that guy, parallel, is equal to 490 newtons. Now, we need to get that back to a number that's related to 100 kilos. So we had 100 times 9.8 gave us that. So if we divide 490 by g, we're going to get us back to this in a mass sense. So we're going to need 490 newtons over 9.8 meters per second squared is equal to 50 kilos. So the amount of weight on a 30-degree leg press that you are dealing with is half of the load that you started with. Now that doesn't mean that everything is the same. This still has the inertia of 100 kilos. It's still harder to start 100 kilos moving and stop it traveling at you than it is to stop 50 kilos moving. So when we start getting into dynamic movements, we still have to bear in mind we're dealing with a bigger mass. But half of the reason you can lift a lot more on a leg press, maybe more than half of the reason, is you're not dealing with the load that you think that you are. If this was to change, let's say we were to use a different angle, let's say that instead of 30 degrees, we had this angle was, let's go 60 degrees, shall we? Let's say mg parallel is equal to mg sine of 60 degrees. Well, now that guy is equal to 100 times 9.8 times sine of 60. And now we have 848 newtons coming down the slope. We divide that by 9.8 and we now have 86 kilos coming down the thing. So the amount of weight that we're dealing with really does depend on how upright or not our leg press is. And that is all because of the physics of an inclined plane. The only thing we haven't included on this, and maybe I'll do this as a separate video, is friction. There is a component on here, depending on these materials, that is fighting against the amount of this that is traveling in that direction. But we'll worry about that next.